Okay. Um, Great. Well, welcome, and I'm really pleased to be here. I get to talk about some of my favorite topics, and yeah, it's a pleasure to follow Ed because some of what I'm going to be talking about. In fact, I'm going to show some slides from some of Ed's papers, and I met Ed in I guess it must have been 1993, right around the time he was publishing that paper that nobody cited. And I went down to, he hosted me at Caltech while I was deciding which grad school to go to. So, yeah, exactly. Yeah, I went to MIT. I didn't know if you remembered that visit, but yeah. Yeah, well, you got over it. We both got over it. So, but but yeah, so what I want to, okay, so I'm at the Center for Earth Evolution and Dynamics at the University of Oslo. It's kind of a weird thing. We call it a Center for Excellence. So we're doing excellent science, and its short name is SEED, and and yeah, it's a center that exists to study the deep interior of the Earth until 2023, and then the funding runs out, and we change directions or something. We'll see. But yeah, so I'm here from there. Let's see. This is my email. If any of you want to, or interested in contacting me about anything we talk about today, later, or you can ask me right during the talk. Just like Ed, I'm very happy to answer questions on the spot. In fact, that makes it a little bit more interactive, so it's not just me talking up here. Okay, so I'd appreciate that. Okay, so today is lecture one of my 3 lectures that I'll give this week. Models of mantle convection. Okay, so what we want to do, we have the surface of the Earth. Now we've been almost everywhere on the surface of the Earth, or geologists have been, and now we have satellites to make detailed measurements of the oceans, and we can map the ocean floor, and we can get a lot of information about the present day Earth. Much of that information, much of the geology that we see from the present day Earth is the result of dynamic processes happening in the interior. So the most obvious thing is plate tectonics, and you can see individual plates here well defined by the topography on their edges. And you can see structures that are presumably associated with deep mantle plumes coming up, for example. There's a lot of interesting seamount structures throughout the seafloors. And then on the continents, we have big topographic features that are built by the dynamics of the mantle. And so what we want to answer is, or we want to ask is, can we understand the dynamics of the interior? And as a part of that, what are the governing processes? What are the processes that form the Earth and cause all this geological diversity that we see on the surface? And how did these processes manifest themselves over Earth history? So we have the geology that we see at the surface that records Earth history, the surface expression of all this dynamics happening as a function of time. And can we pick that apart, understand how the mantle was moving and evolving as a function of time? And in order to do that, we have to develop models. Okay, so I'm going to talk about modeling of mantle convection today, what goes into those models, and what we can get out of those models. Okay, so we have this picture of the Earth now, and we know it really well. So what we want to do is fill in all this space here. So this is a plot from the present going back to the beginning of Earth. So this is time on this axis, and this is depth on this axis. And we are at the surface. We know this point really well, this point, which is the present day at the surface. That's that picture. And we know that really well. Okay. As a function of depth, we can ask Ed how we can get that, and we can get pictures of images or a lot of detailed structure information about the present day Earth right now. Okay, so we can get from the surface, maybe it gets less and less resolved as you go deeper in the Earth, but we have a detailed picture of the Earth right now. Okay, and then we also have geological observations at the surface, and we have them going back in time to some distance in the past. Okay, and obviously they're better right now, and they get worse and worse as you go back in time. This is a geological map that was, I think that should be 2018. I'm sorry, and these are all different time periods. So the colors represent the age of the rocks at the surface there. Okay, and there's obvious patterns in the oceans that we think we kind of understand, and then there's more complicated patterns in the surface that represent some much deeper time. Okay, so we have that, and the rest. Okay, so we have this axis getting worse as you go down, this axis getting worse as you go back, and the rest is the domain of models, and that's what I'm going to be talking about today. So if we want to understand anything off of one of these two axes, we need to use models. Now, models can mean a variety of different things, right? In fact, in a sense, the talk yesterday presented a model. What he was doing was presenting a model for how the Earth works. And it wasn't a numerical model, and it wasn't an analog model. It was a kind of descriptive model that he used in order to explain the patterns that he observed. And so that's one type of model. We can do models like this one. This is a simple model where you have a beaker. It has corn syrup in it. Does everybody know what corn syrup is? I realize that, you know, if I give this talk or I give something like this, teach a class in the United States, everybody knows what corn syrup is. But here I gave something similar in a class in Oslo, and they didn't know what corn syrup was. So corn syrup is it's like honey, but it's an industrial product that's made from corn, and it's basically a syrup. And so it flows. If you dump this out, it would flow out. And you can think of it like honey. Okay. If you heat the bottom of this beaker, this is like a flame or something, then what do you expect will happen? Heats up, and the material rises in a plume. And that's, I don't know if you expected that or not, but this is telling us, this is a model of a form of convection. So if you heat a viscous fluid from the bottom, at least in these circumstances, you're going to get plumes that rise up. And that's an interesting observation, and it might have some applications to the Earth in terms of how we understand the intraplate volcanism in a place like Hawaii. Okay, so this is in a sense a model of mantle convection because it's a representation of some aspect of mantle dynamics. So it's a representation. It's a way of describing the mantle. And a model should be useful in some way for understanding these dynamics. So the talk yesterday presented some kind of a framework for thinking about the dynamics of the mantle, and it was useful for doing that because it explained these various observations. And a model should be testable, at least in some way. It should make some predictions that you could test with actual data. And there's a quote that I think is useful. All models are wrong, but some are useful. If you look on Wikipedia about this quote, there's several different ways that this guy, George Box, who was a statistician, described this. But obviously, this plume experiment in corn syrup is not the mantle. So it's wrong. And the mantle doesn't heat this way. You know, mantle might heat more uniformly at the bottom. And so there's a lot of aspects of this that are not representative of the mantle. So you could say, well, are those important? These are questions we could discuss. Are those important for the representation of this model in terms of understanding the mantle? And those are discussion points and things that would need to be figured out. But yeah. So that's something to keep in mind as I go through this talk and present a whole bunch of different models of the mantle dynamics. Is that all of these are wrong? They're not actually the mantle, but how useful are they in terms of understanding what's going on? Okay. All right. So I'm going to start really basic about how convection works. And I'm not going to spend too much time on this, and I'm going to get quickly into how it works in the actual mantle, but we have experiences with convection in our everyday lives, a pot of boiling water, for example, and they all work the same way, that you have some source of heat, and at a certain point, it gets most useful, or the fastest way of getting the heat out through a layer is to actually take pieces of the hot material, which get less dense as they get hotter. So they get lower density and they rise up. And it's quicker to actually bring the material from the bottom where it's hot to the surface where it's cool, and then then it gets dense and it sinks back down. It's quicker to do that circle than it is to diffuse the heat across. Because in most rocks, for example, diffusion is quite a slow process. So for the mantle to bring heat all the way from the bottom to the top, it's much easier to make a plume and bring it all the way up rather than wait for that heat to go all the way through the mantle. Okay, and you can show this with various equations. This is a lava lamp. This is often been used as a representative model for the mantle, in that you might have a material that has a that's chemically different than the surrounding material, and it shows interesting dynamics as it heats up and becomes less dense, and then it gets to the top and it cools down and sinks back down. And this is an example of double diffusion, thermochemical convection, where you have chemical differences and temperature differences going on at the same time, and that might be important for understanding parts of the mantle. And this is Miso Soup. If you look at Miso Soup, it's really interesting. These lines here, like this, are cold downwellings, and what happens in Miso Soup, at least in this picture, and I think most of the time, is that you get linear cold downwellings, and they tend to surround upwellings that bring the starch or whatever's in Miso Soup up to the surface. So so you can see interesting patterns. You can see that in like a pot of boiling spaghetti water and a lot of different things. Yeah. Oh, am I doing this wrong? Oh. Put this in the other pocket, maybe, like this. Ah. Okay, is that better? Obviously, I'm not experienced with this part of the presentation. Okay. Okay, so that's convection in fluids that we know. I guess right before the first experiments that I ever did as a scientist, and this is when I was about 19 years old, I think. It was right before I met Ed. So I was younger than all of you. I was an undergrad assistant in a laboratory at University of California, Berkeley. And the grad student who was in charge of this had me I was helping with the fluid dynamics experiments that they were doing there. And so what we had was a tank. It was 1 meter by 1 meter square. So like this, square, and 30 centimeters high. So you can imagine how big it was. And it was filled with corn syrup. So we actually went to this, I remember we went to this railroad yard, and they had giant tanks of corn syrup in the railroad cars, and they opened one of the nozzles on the bottom, and it just kind of shooting out, into these buckets we had, and then they closed it up. So they would just waste this much corn syrup. They use it to make candy and things like that. So it's an industrial product. But we used that corn syrup that they gave us to fill the tank, and then we had this heating system where we put hot fluid through the base of through a water channel through the base of the tank. So we heated up the base of the tank. And just like in that little experiment with the plume, the beaker, you had plumes coming off the surface. And what you're seeing here is, if you had one of those old slide projectors, it was shining in through the tank and then coming out on a screen on the other side, and then we'd take a recording, a film of what was happening. We'd record it on these VHS cassette tapes. So this was 25 years ago. And so we have this, and what you observe are plumes coming up, and these are the shadows of plumes. So they come up and they change the index of refraction. The heat changes the index of refraction of the material, and it bends the light as it goes through the tank, and you see these shadows of plumes. And as the tank heated up, so this is 20,000 seconds, this is 56,000 seconds, and now the tank is all much hotter, and the character of the plumes changes. You can see now they're a bit thinner, and then if you get up to 88,000 seconds, they're even a little bit thinner. And what my job, okay, so I helped in the laboratory with setting up this tank and coming in overnight to maintain it and stuff like that. And the other job I had was to take these recordings and watch them and then measure, even with a ruler on the screen, like how big these plumes were as a function of time, in order to see how the changes as the plume heated up, how the character of the plumes changes. Okay, so what was happening is that the character of the convection was changing as the tank heated up. And so what you can do is express that in terms of this parameter called the Rayleigh number. And the Rayleigh number here is, okay, I can go through the terms. This is the Rayleigh number. It's a dimensionless parameter. And it's a parameter that we use to measure the vigor of convection. Okay. The first term is the density of the corn syrup. And I put values here that are for the Earth. Okay, G is gravity, that's about 10 meters per second squared. The thermal expansivity of the material, how much, as you heat up the fluid, what fraction of expansion of the material do you get? This is the temperature difference across the layer. For the mantle, we can say maybe 3,000 degrees Kelvin. The depth of the mantle, this was 30 centimeters in our convection experiment, but for the mantle, it's almost 3,000. Thermal diffusivity, 10 to the minus 6 meters per second squared, and mantle viscosity. And I wrote 10 to the 21, although there are huge variations in mantle viscosity. And actually, what we found is that there are huge variations in the viscosity of that corn syrup also. As it heated up, the viscosity of the corn syrup decreased. So I also had to do experiments where we took a sample of that corn syrup, and you have to measure the viscosity, which is a very time-consuming process. But it involves taking a beaker of it and then moving a disc within it and measuring the force that it takes to move the disc. But it's hard to get it to be stable and things like that. So we were able to measure the Rayleigh number for that. If we knew the temperature, then we could calibrate the viscosity. We could know everything in this Rayleigh number, and we get the Rayleigh number as a function of time. So just for comparison, the Rayleigh number for the mantle, if I use these numbers, I get 7 times 10 to the 7th. And it probably should be a little bit less, because this viscosity is maybe appropriate for the upper half of the mantle, but the lower half is probably more viscous. So if somehow you average it out and you get a lower number than that. But I guess in the introductory geodynamics class, you would be able to show that if your Rayleigh number is bigger than this critical Rayleigh number, which is about 657, then you will get convective flow. Okay, so the mantle is obviously much bigger than, the mantle Rayleigh number is obviously much bigger than that, and the mantle should be convecting then. In fact, it should be convecting vigorously. Okay. All right, so here this is the same plot, but instead of time, I'm plotting the Rayleigh number as a function of time. And so you can see the Rayleigh number is increasing. As the Rayleigh number increases, the character of the convection changes, that the plumes get thinner. And in fact, this is the result of all that, looking at the video screens and measuring plumes, is that as the Rayleigh number increases along this axis, this is the plume radius. And so this is the radius of the heads, that would be something like this, and the radius of the tails, something like that. And so you can see that the head radius goes down and the tail radius goes down. And we developed a scaling relation and so forth. Okay, so that is convection. So this is, we were able to develop kind of, with these expressions, this would be kind of like a model for how convection changes as the Rayleigh number changes, and you can apply that to the Earth. I'm sorry, what's the question? Oh, yeah, that's a good point. It's a layer very much like this. That calculation with the 657 assumes an isothermal bottom and an isothermal top. So a hotter bottom and a colder top. And if you had something else like heated, instead of a hot bottom, you'd have a like an internal heat source in the interior, then you could also calculate a Rayleigh number for that, and you would get something different. Yeah, if you have, I think the question you're asking is if you have thermochemical convection, or maybe a layered convection or something like that, if you have additional complications to the convection pattern, then yeah, you would need to do a different analysis and you'd get different numbers. So, any other questions about the Rayleigh number? Yeah, probably more than one. Yeah. Yeah. Yes. Yes. Mm-hmm. Yeah. Mm-hmm. Yeah, that's right. Yeah, that's a good point. That's a good point. The other things the measurement of the temperature, you see these shadows here, that's like what we did is we poked a hole up through the bottom, and so we could have a temperature sensor in there, so we're measuring the temperature in the interior. And what we found that the plumes actually came up it would initiate plumes up that structure. So that we actually couldn't you'd see the plume coming up, and so you'd get extra plumes there. So in a way, that temperature measurement is affecting your measurement of temperature because you're always having extra hot material coming up. Yeah. Mm-hmm. Yeah, right. So on the edges, you would typically have a downwelling on the edges because there's coldness on the edges. So you'd have a circulation that was generally kind of like this. So that's another complication. Yeah. So it was an interesting experiment, and I learned a lot about convection from doing this type of work. So yeah. Okay. So if we want to get away from those complications, or if we want to be able to, instead of sticking a temperature probe up and then affecting the convection circulation and things like that, it's just much easier to do it in a computer. I mean, you don't get your hair sticky with corn syrup and things like that, and the computer stays up all night instead of the undergrad. So yeah, we can do experiments. If you call them experiments, we can do simulations of convection in a computer. Okay, and this I actually somebody gave me some slides that I would teach the class for them, and this was one of the slides. I can see a citation there, and that's all that is on the citation. So hopefully this is accurate. There's no date or first name, but oh, okay, it's from your website, so it's probably legit then to use it. Okay, good. I was a little worried because I didn't know where it came from, but this is Rayleigh number of 10 to the 7th, and I'll play the movie. Oh yeah, there. Okay, and you can see interesting plan forms at the surface. We have red upwellings, hot, and cold downwellings. You can see the character of the convection changed as the system kind of ran to steady state. You get bigger spaces between the upwellings and the downwellings. So that's interesting. And so this would be a model of convection. So is that an isoviscous case?
Yeah, it's the
simplest case. Good, yeah. So that's the simplest case you can have. And you can say, well, this has a Rayleigh number of about what the mantle should have. It's not in a sphere, so that's one thing that's different. We think that the mantle has internal heating, and I don't think this has that. And the Earth also has plates, which are very stiff. And that actually changes the character of the convection a great deal. But this is Rayleigh number 10 to the 7th convection, which is analogous to what the Earth has. So in a way, this model is useful for understanding what convection at that high Rayleigh number would look like. And then we can do more, we can add complications to this as we need to in order to understand things like how does plate tectonics work? How do we get mountain ranges from the convection? Things like that. Okay, so in order to make this calculation, we need to solve basically the equations of fluid dynamics in the computer. So to do that, there's several steps, and I'll go through them one by one. First, we need a model that solves the equations of the basic physics. And so I'll just write these out really quickly. The first is that we have to conserve mass. So the gradient of velocity is 0, assuming that the material is incompressible. We need to conserve momentum. So this is the Navier-Stokes equation. You've probably heard of the Navier-Stokes equation. This is one way of writing it. This is, you have a pressure gradient. These are viscous stresses. A body force is gravity. For convection in the mantle, it's gravity. And so that would be, and the sum of these things is equal to the inertial forces. For the mantle, this term is 0 because there's no inertia really for the mantle. Everything's in static equilibrium at all times. And you can show that by comparing the amplitude of these different forces. This force would be much smaller than the others. Okay. For other fields, like oceanography or atmospheric sciences, they also use this same equation, but for them, typically this term would be unimportant and this term very important. So this is the viscous stresses, and the viscous stresses, the viscosity of water or air is low enough that this term becomes much smaller than the others. Okay, so that's interesting, and at one point I was thinking, well, I'm solving the Navier-Stokes equation, maybe I could do that get into atmospheric sciences or something, and it's actually the solution methods and things like that are very different. so it's interesting to think about that, but in practice, it's very different. Okay, and then finally, energy conservation. So we have a temperature change in time. This is a velocity. This is a flow across a temperature gradient. So you're kind of moving the temperature gradient, and then your temperature at any one place would change with time. This term here is diffusion of heat. That's the case where you have a hot thing and a cold thing, and thermal diffusion brings the heat from the hot thing towards the cold thing. And then the last is heat production. So typically for the mantle, that would be radiogenic, a radiogenic source of heat. Okay, so we have those three equations, and we need a way to solve them in the computer. And there's several different ways to do this, and I'm not going to really get into that. Often what you do, there's actually a lot of different ways to do it. Often what you do is you set up some sort of grid like this. I like this one. I've heard Paul Tackley call this a yin and a yang way of setting up a grid. This basically what you do is on the grid points, the interaction between these grid points, you solve these equations. Okay, and I'm not going to get into the details of how to do that here. But this one problem you have, you can't, when you're doing it in a sphere, is that you can't just use latitude and longitude lines because the longitude lines come together at the pole. So you need to do something in order to get a relatively uniform grid to represent itself on a sphere. And so this is one way of doing that. Another is to break it into different chunks, and that adds complications and takes away different complications. One of the reasons this works so well, and the people who make sport balls for sports also use a similar type of way. If you have to cover a sphere with something that isn't too curved, then, or if you have to cover a sphere that's something with a kind of a regular rectangular shaped geometry, which would be easy-ish to cut out of a flat cloth, then you can do that with this yin and yang structure. That here's tennis ball and a baseball, for example. Okay, so that's a so we're solving these equations in some representation of the mantle like that. We need to make major assumptions about what we know about the interior. For example, we don't know the viscosity and how it varies with depth. And so we need to make major assumptions about that. So, and how does it vary with temperature? How does it vary with these different compositions of materials? There's a lot of things we don't know about the interior, and we have to make assumptions on them and we set those into the model. Now, one thing we can do is run the model a whole bunch of times, changing those assumptions, and we can see how these parameters affect the results. And I'll show some examples of that. We also don't know the starting condition. So if we want to run our model forward in time, we don't know what the condition is at the start to get to where the Earth is now. So there's different ways to handle that. You can run using the Earth condition right now. Maybe we do this from seismic, estimate this from seismic tomography. And tomorrow in my lecture 2, I'll show some examples of that approach, of using, just basically using information that we know about the Earth now and trying to predict other observables that we have on the Earth now. Okay, so just everything in the present day. And we can try to run our model backwards in time. So essentially that's like reversing gravity, and maybe I'll show some slides about that. Or we can guess at the initial structure and run it forward in time and hope that we get to the present day. Or we can take a different approach. We'll say, look, we don't know what the initial condition is. We want to understand convection generally. And so let's set up a model kind of like that one that Stefan did, where we set up a model and let it run for a long time and see what the general patterns are and see if those general patterns represent the general patterns that we see on the Earth today. And so I'll be talking mostly about that type of modeling approach today. And then later in the week, I'll try to get more into actually predicting the specific things that we see on the Earth. Okay, so, but for that, we're going to need to make assumptions about about these parameters. We can change them. And in a sense, if we run our model long enough, then maybe it doesn't remember the starting condition. And so it doesn't matter about the starting condition. That's not always true. Okay, and then the other thing is that we have to realize that we're going to have to make some major simplifications about the Earth. For example, this paper, Stadler et al. 2010, they're using very high resolution to try to resolve the deformation happening in a subduction zone. And what they found was that this detailed deformation happening in there does affect the large-scale convection, the large-scale patterns. And so you need some sort of way, and they developed this, of finding out the areas that have intense deformation in the Earth, getting really high, telling your code to put really high resolution there, and then use lower resolution where you don't need to resolve things as detailed a way. Okay, so what they've done is develop this super high resolution model, but even this resolution is maybe 5, 10 kilometers, something like that, and that's not even as detailed as a fault zone on the Earth. So you're going to have to realize that any model you make of the Earth will have major simplifications. And generally, we're going to have to ignore or summarize in some way the complexity that the Earth has. Okay. And then finally, getting back to that quote I showed before, our model should be useful in some way for understanding the Earth. You could put a whole lot of complexity into your model, and it would give you some result that might even look like the Earth, but it's not necessarily useful if you don't know which part of that complexity is producing the structures that you see, the actual observable that you're trying to model. So if you have a model which has everything in it, you don't know what part of that everything is affecting the behavior. And that's really what we want to get at. So that is going to make the model useful. If you can make a simple enough model that produces the behavior, then you can understand what is actually producing the dynamics that you're interested in. And it should be testable in some way against some sort of observation. Okay. All right, so I'll go through a couple of different examples of Mantle models and add complexity as we go. Okay, so these are also very simple models, but this time they're in a sphere, and it's changing the Rayleigh number. So here we have 10 to the 4, 5, and 6. And so just like those plume upwellings that we had in the convection corn syrup tank, you can see that the plumes get narrower as you raise the Rayleigh number. And this is true in a sphere also. That's what we learned from this. And using the analysis of Rayleigh number, we can show that the reason this happens is this boundary layer thickness. That's the thickness of the layer that's being heated up on the bottom and cooled down on the top. That scales as with the Rayleigh number to the -1/3 power. So as you increase the Rayleigh number, this gets shorter. So you can kind of see it here that you can see that thickness here in the temperature contours. It gets thinner, and then high Rayleigh number, it's quite thin. So at the and so for the Earth, with Rayleigh number 10 to the 7th, we have a boundary layer of about 100 kilometers. Okay. The velocity of the surface motion should scale with Rayleigh number to the 2/3. So as the plates, that's the typical velocity of the material. As the Rayleigh number gets larger, the material is going to move faster. And finally, the heat flow scales with Rayleigh number to the 1/3. So that's as the Rayleigh number increases, you get more and faster heat flow coming out. And that's important to understand this. This relation here is very important for understanding how the mantle evolved with time in terms of its temperature. So if you, for example, as the mantle cools, its Rayleigh number should go down because its temperatures are going down, its viscosity therefore is temperature dependent, that should go up, and so the Rayleigh number gets larger. And so the convection would slow down as the Rayleigh number decreases. That means the heat flow should slow down. And that decreases the rate of heat coming out of the mantle and causes the Rayleigh number to not drop as fast. So it kind of stabilizes the mantle convection. Okay, let's change another thing. Let's change the size of the core. So if we do that, this is different core sizes. You can see the core here. This would be a planet more like Mercury. And this is keeping the same Rayleigh number. I can't remember what the Rayleigh number is, 10 to the 5th. What you can see is that the spacing between upwelling and downwellings typically decreases as you go towards higher core size. And that's because the thickness of the mantle is increasing the, the scale of of this spacing scales as the thickness of the mantle. Okay, so you have an aspect ratio a little bit bigger than 1, between 1 and 2. Okay, and then somebody asked about internal heating earlier, and this is an example where the authors have added more and more internal heating for 2 different core sizes. So just compare this column and this column. And so you're increasing the amount of internal heating, and this has got a lot of internal heating. And what happens is that the effect of the lower boundary layer gets less. The whole fluid heats up, and you get fewer upwellings with internal heating. That's because there's no boundary layer for them to rise up out of. Because you have internal heating that's heating the whole thing up, and that's where your heat's coming from instead of from the bottom boundary. And so instead, you have a convection system that's dominated by downwellings. Downwellings in bringing the cold material from the surface down into the interior where it can heat back up. Okay? So instead of heat being transmitted all across that layer, it's being transmitted from the interior of the layer towards the surface. Okay. All right, and so this might be something that is important. This is important for the Earth because if we have more internal heating as a heat source for the Earth, we'd have a convection system more like this, which is dominated by downwellings and very few plume upwellings. But if we have something that's mixed, like this or this, then we'd have some upwellings and some downwellings. Okay. All right. What about the tectonics at the surface? Okay. Here they've this is Tackley 2000, where they've used a viscosity. They've imposed what's called a yield strength. So if the stresses somewhere in the calculation exceed some value, which is an assigned value of the yield stress, then the material weakens. It's kind of like if you have a paper clip and you bend it, and if you bend it enough, then the material heats up and then it eventually weakens. So you're exceeding some strength value of the material and you get it, and it weakens. Okay, so if you have a very low value of that, then you get deformation that's kind of happening everywhere, and it doesn't look very plate-like. If you have a very high value, then you can never break the surface, and you get little drips coming down. So this is called a stagnant lid. It might be important for Venus or Mars. And you get these little drips coming down underneath a rigid plate. So the Earth is somewhere in between these, where we have zones where there's a intense deformation at a plate boundary, and then big rigid plates outside of that. And so you need kind of an intermediate, at least in a mantle model, if you use an intermediate yield strength, you can get plate-like behavior. But there are some complications there's some aspects of this that are not very Earth-like. For example, here you have kind of this would be a downwelling. You have a symmetrical downwelling. And subduction really happens in one way rather than 2 ways. So this is a little bit different than the mantle in that respect, but you do get plate-like behavior. Okay, these are 2 calculations. This were done by Fabio Cromeri, who's at SEED, where I work, gave me these. The first one I'll show you, these are 2 movies, and they have they're basically the same calculation with one difference on the top boundary condition. This is a free slip condition. That's Normally we think of the Earth as having a free slip. The plates are free to move wherever we want. But this, in the computer, we can't, it's not easy at least to allow them to move in the vertical direction because you set that finite element grid, and so you're forcing it to stay on the surface of that grid. You're not allowing it to move up and down. So they're free to move sideways all they want. And here's the calculation. Is it going? Yes. Okay. And so here you have upwellings. You don't see a lot of things you see a lot of plumes, and they're kind of burning into the surface, but there's not a lot of surface motion. And what you get is stagnant lid convection in this particular case. Now I'll show you another case, which is basically the same, but now you have a free system where he's devised a way to allow the material to move up and down. And what you'll see right here is, I think it's right here. Yeah. Now it started a one-sided subduction coming down. And so you can see that kind of does look like, here it's zippering down, that looks like a subduction zone. And so these two calculations are the same except for that specific boundary condition. You're letting it, in this case you're only letting it move sideways, here you're letting it move vertically a little bit also. And so that one thing makes a big change, not just in particulars about the surface, but the whole convection of the whole system is different. Here you're stuck with little upwellings. And in this case, you can get flow that replaces the material that's being lost on the surface, and the whole dynamics of the system change just from that one change in the boundary condition. So that's important to keep in mind as you consider all these different models. Okay, this is a calculation. I was at a thesis defense. I actually wasn't there. I was controlling a robot that was witnessing the thesis defense. This is 2 weeks ago, and the person that was defending her thesis was Melis Arnaud, and she told me that it would be, first of all, okay to use this in the this is an actual movie that was taken from the PowerPoint presentation that she sent me so that I could view everything in real time as I witnessed this defense. And first of all, she told me it would be okay to use this. She also told me that she was a student at this conference, at this workshop, a couple years ago. So now she's defending her thesis. This is a calculation that she developed that has plate-like motion. So what I'm showing here is viscosity. You can see low viscosity in the plate boundary regions, high viscosity in the plate interiors. And so this kind of looks like plates moving with, this would be like a spreading ridge, and there are other places where there would be a subduction zone. This is using the yield stress approach. And we can ask the question, how representative of plate tectonics is this? And how can we test it? Does anybody have any thoughts about what observations from the Earth that we could use to test if this has the characteristics of Earth's plate tectonics? Yeah. Yeah. Mm-hmm. Yeah, so like how fast are the plates moving? Yeah, that's one way. Yeah, that's good. Yeah, so it's this plate, like, and we could even go farther than that. Instead of just the average, the distribution, you know, on the Earth, some plates are moving faster than others. And so there's some distribution of plate velocities. It's interesting, it's bimodal, that there's a group that's moving fast and a group that's moving slow. And do you see that distribution in the plate motions? Any other thoughts? Of the plates, yes, yeah. So some on the Earth we have some really little plates, and we have some really big plates, and so there's another distribution there. So that would be another thing. I thought of at least 4. So we have 2, and I did think of those 2. Any others? comparison of the heat flux. Yes. Yeah, you could. Yeah, you could do that. We know the heat flux of the Earth pretty well. So yeah, that's actually one I didn't write in my list. So that's good. Yeah, that's good. Other thoughts? Yeah. Yeah. I'm sorry, what was the last part? Yeah. Yeah. Yeah, so you can use seismology. The seismology would give us some sort of image of the interior. Is that what you're meaning? That we could then compare to the images under that? That's one way. Yeah. And you had one. Yeah, the gravity anomalies. Yeah, you could use that to predict the gravity anomalies and see if they're related to subduction zones or okay, these are all ones that weren't on my list, so that's good. Any others? Let's see. I'll show you my list. Oh, yeah, I meant to, yeah, so basically, all mine were confined to this, although if we use some geological observables, we can maybe move it back that way. Your suggestion was to use information from that axis. We have images like this, which is the strain rate for the present day. So these are the plate motions, and so this is the strain rate for the present day. So some places, like these plate boundaries, you have really intense deformation in a short area, and then other places like the western U.S. or this part of Asia, you have more distributed deformation, and where your strain rate is less, but it extends over a wider area. And so you can see that this calculation has areas where there's some width to the plate boundaries. And so is the distribution of the width of these boundaries, which it's different for different parts of the Earth, is the typical distribution similar to what you're seeing in here? And so that's okay. And another thing to keep in mind, and this is true with seismology also, is that, well, I'll just say the title of this paper, which shows the second invariant of the strain rate everywhere. It's called A Geodetic Plate Motion and Global Strain Rate Model. So this itself, we're taking that as an observation, but it's itself a model. And seismic tomography is also a model. So that's something to keep in mind, is that maybe it's a very useful model, but it's still a model, and so it has its own uncertainty and variations of quality of data that go into it in terms of constraining that. Okay, here's my list finally. So spacing of plate boundaries, the plate size, dimensions of plate boundaries, the length and the width. Yeah, that's another one that these, like, there would be a typical length of a subduction segment or a ridge segment, and then if you add it up over the whole calculation, how does that compare to the length and width of plate boundaries on Earth? The plate boundary type, ridge, transform, and subduction, is the distribution between them similar to this calculation compared to the Earth? And the deformation rates, which gets at the plate motions, but also the rates of deformation in these areas. If we go back in time along that horizontal axis of that map of that graph that I showed, then you can use information like this, which is a model again of tectonic reconstruction as a function of time. And so here's Pangea, and eventually it breaks up. That's going to change the length of the ridges, the length of the subduction zones. All those things are going to change with time, and maybe the rates and speeds of the plates too. Do we see those kind of cycles in the models? That you have Um, okay, so this basically, this calculation, this is for the present day, but we could get something related to that with this tectonic model as a function of time. And so it would allow us there to start to fill in, to use geological observations near the surface that we can get from the tectonic history to constrain models. So you could kind of start moving along this axis to constrain models. Oh, let's see, how am I doing with time? Yeah, okay, about a half an hour left. Okay. All right. Seismic tomography. Again, that's a model of the interior of the Earth in terms of shear velocity variations. And this is one cross section across a great circle that moves like this. It goes from across Asia into the interior of the Pacific. And so you see some interesting patterns here. This is the subduction zone that's right here. You can see it very nicely, and then it does something different at this depth. And in the central Pacific, you see all this red stuff. That presumably means something in terms of the convection patterns. So we can say, well, the first thing is to ask, well, how are the slabs connected to the deep mantle? And it seems like, at least in places, they might go through. Here you have this is clearly connected, but how is this connected to the deep interior? The first images, I remember when I was a grad student, there was a big debate about whether or not the mantle was convecting separately between the lower mantle and the upper mantle. And the reason for that is there's that big discontinuity at 670 kilometers depth. And then seismic tomography started to become well enough resolved in kind of the mid-90s, late 90s, that you were able to see indications that the slabs went through the 670 discontinuity. And so that people said, well, it's got to be whole mantle convection because the slabs are going through. And now it seems a little more unclear because they're deflected in certain ways. And it's not obvious that a slab, that an image of a blue thing going all the way through would necessarily mean that the mantle is convecting separately. Is that it's whole mantle convection. For example, you could have thermal coupling between the layers. This is a paper from 1988 where they did a fluid dynamics experiment where they were basically showing this. They had upwelling and then downwelling. This cold stuff then cooled off the top of this boundary, which made another downwelling. And so if you did seismic tomography on this, it would look like a slab going all the way through. But in fact, these two layers are convecting separately. And what you need to have is here in this place here, you have flow going that way and that way. And that's kind of hard to do with a very viscous fluid. But if you had some way of decoupling these layers in terms of mechanical decoupling, you might be able to get something like that. This is what we normally think of in terms of two layers convecting separately. You have a downwelling, and then that moves this way here. The two are going, they're mechanically coupled, so they move in the same direction, and you have your downwelling here. So this would spread out and move down. So we probably don't see that, but that one is it's not obvious that you can rule that out. Okay, but we do seem to see deflections at 670, 1000. What do those mean in terms of the mechanical properties of the material with depth and the large scale convective motions of the mantle? Okay, and what are these two slow velocity regions on the core mantle boundary? And the talk yesterday gave a name to these that's often used, the large, low, slow velocity provinces, or LLSVPs. They're large. They have low seismic velocity, and there's two provinces, one beneath the Pacific, which is shown here, and another one beneath Africa, which is shown here. They're opposite ends of the Earth. Okay. Yep. And so here I'll just, maybe Ed will talk about this later in the week, but this is a picture from one of his papers, 2016, where these are different different convection interpretations of these two large low slow velocity properties, LSVPs. One is, for example, that they could be a whole big bunch of plumes that are coming up in the same place, and when you do seismic tomography on it, it looks like a big red blob in LSVP. Another option is that it's kind of like the lava lamp. Another option is some sort of pile that's dense and it sinks down and you get slabs pushing on the sides and they drive up plumes. Or maybe it's a little bit more raised up and you have internal convection in that. So these are different images, and from the seismic tomography, maybe it's hard to distinguish between them. So in a sense, we're using, these are different models that have been put forward to interpret seismic tomography. The images that we see just for the present day. So how are we doing to fill in our domain of models? We have the tectonic history going back. We can use that as a constraint. Subduction dynamics, whether or not slabs are deflected at 660 or 1000, and how are they connected to this tectonic history? So the tectonic history should give us information about the surface, but also with depth, as we can predict where the slab should be sinking. That's why I drew this in kind of a tilted way. And then lower mantle dynamics. We can develop models of lower mantle dynamics, and maybe that gives us some information about how things move backwards in time. We have constraints from volcanism on the Earth. And I'm not going to get into this because I'm not an expert in geochemistry, and it's better for just having geochemists talk to you about that. But as I understand it, mid-ocean ridges and ocean islands have rather different geochemistry. And so maybe they're sampling different parts of the mantle. And then if you think about that, then you have to think about what the ocean islands are actually sampling. Are they coming from, this would be the layered convection system where you don't have a mixing between these two the upper mantle and the lower mantle, and the ocean islands are just sampling this lower mantle, which is huge. That would be an older view. These views are maybe more like what I just showed you, where you had big piles, maybe at the LSVPs, slabs coming down between them, and the ocean islands sample that. This has been proposed where you have little blobs of primitive mantle that are floating around in the mantle, and they don't really very often get sucked into a ridge. And so you have all these different different possible explanations for this observation that ocean islands and mid-ocean ridges sample different things, different reservoirs. But you can also ask, well, which of these is consistent with the seismic tomography or the slab dynamics that we see or that we are modeling? Another volcanism example you can use is to think about where the edges, where the hotspots are positioned on the surface of the Earth. So this is a plot of all the major hotspots, probably more than all the major hotspots, some of the minor ones too. There's Afar, Hawaii, for example, Iceland. And what Torsvik et al. Noticed in 2006, at least if you look through their eyes, they would suggest that most of them are coming from the edges of these two LSVP zones on the base of the mantle. And depending on how you count, what you consider a hotspot or not, you can do the statistics on this and determine if that correlation between the edges of the LSVPs and the locations of the hotspots is robust or not. You can go farther and look at the large igneous provinces, which are the big flood basalts. For those, they've been moved by plate tectonics to some other part of the Earth, so you have to do a reconstruction back to where they would have been erupted. But if you do that, you find that a lot of them are also on the edges. And then he even did this with diamonds. Diamonds, the place where you find kimberlite mines, for example, these are in Canada. The black dots on here, the black dots and the white dots are the kimberlite areas where you find diamonds. And these also possibly are associated with the edges of the LSVPs. So the stars are the hotspots with a deep origin. The circles are the large igneous provinces. All these things are associated with some sort of intraplate volcanism that seems to be associated with the edges of the LSVPs. Okay. The way they explained it, the model they created to explain these observations, is one that's actually related to the model that you saw yesterday. Is that basically you have these two LSVPs, and the edges of these LSVPs are conducive, for some reason, to producing hotspots, or producing plumes. So the plumes tend to rise from these edges of the LSVPs, and the LSVPs, because we see these geologically, this volcanism from the distant past that also arose from these same edges, that we can infer that the LSVPs are stable over some geologic time period, about maybe 200 million years. And the thing that keeps them there is that you have a circumpolar belt of subduction. So that's the blue belt here. And this is seismic tomography from the lowermost mantle, 2,800 kilometers. And so you can see that the seismic tomography at least suggests that there's a lot of slab material down there. And their idea is that you have that subduction's kind of always happening on that belt. It sinks down and it pushes this material over to the edges of these piles, and the plume, and it also pushes plume material up from the edges, and then that forms the intraplate volcanism. But this would imply that the piles are relatively stable, at least for some period of geologic history. If you look at models of mantle flow, models that have piles, you don't always see plumes coming up from the edges. So that's an interesting question. For example, here they seem to come up from the middle of the piles. This is a calculation McNamara et al. I think Ed might be one of the et al. And you also see this is as a function of time. The piles tend to separate and move around with the flow. And that's kind of what you'd expect from thinking about how convective flow from the models of, for example, the flow of Rayleigh number 10 to the 7. It's rather chaotic. And so things would tend to move around. Okay, so we asked the question, well, what does it take to keep a LSVP stable? So this is a paper published this year by a grad student that's working with me, Bjorn Hein. And what he did was he set a stable boundary condition at the surface, which would be basically surface motions that are moving like this. You have one plate that's moving like that. That generates an upwelling here and a downwelling here and a flow in a circle. And that makes things very stable. And so what you get is an LSVP under the upwelling. And that's kind of what you'd expect. All this dense material gets pushed over to the edge. You're starting with this layer of dense material. And we're able to change the density of it and the viscosity of it. And so, and we impose the stable plate motions at the surface. And it's interesting that what you see from the plumes that come off is that you have the boundary layer gets thicker and thicker as you move away from the subduction zone. Eventually it becomes unstable and rises up, typically on the edge of the LSVP. And when you do that, you can see here, this is a plume coming, this is a former plume, and this is one that is still forming. And these are in sequential, so this is this plume, later it moves up, and there it is there, and you start the cycle again. So you have a series of plumes coming up one after the other. And the LSVP, which is highlighted here, has some interesting behavior that as a plume approaches, it squeezes in, and then once the plume leaves, it relaxes, and now it's going to get pushed in again. And so it kind of pumps itself like that. So that's interesting, and we can look in the geologic record maybe at the frequency of plumes in order to try to constrain this model. Okay. And the other thing we found is that not all LSVPs are stable. So for example, here these have the same density, that's that V param. Oh, sorry, this is the B a little bit less. The density in this one is a little bit less, and the viscosity is a little bit less. And you can see that this is after the same amount of time, I think, and this one has maintained its shape. It's still a coherent pile, where this one has been smeared out around the calculation. So the pile falls apart. Here the pile is stable, here it falls apart, and you can map out the parameter space. If you do enough of these runs, these are the ones that would be stable, metastable, and unstable down here. And this is the density of the pile, and this is the viscosity. So if you have higher density, then the pile becomes more stable down there. If you have a higher viscosity, then it also can make the pile more stable. So you typically need some cutoff. You need some cutoff of density, but after that, the stability depends more on the viscosity, actually. Okay. This tests if the pile is stable in time, so does it get sheared apart? But it doesn't test the positional stability, because we haven't really allowed these things to move around, because we haven't changed the surface motions. We're keeping that constant. So that's a big assumption. This is in the supplemental material of that paper, where he did an experiment where he made a pile like this and then reversed the direction of flow. And if you reverse the direction of flow, sure enough, then the subduction goes down on top of the pile, and it eventually pushes the pile to the other end. And if your density and viscosity are high enough, it can be stable there and doesn't get mixed in too much to the calculation. But it's really controlled by the surface tectonics. So it might be that the stability of these LSVP zones, if they really are stable, then we need tectonics at the surface to have a relatively stable configuration. I'll talk about that on the last day, on Thursday. Yeah. All of these piles are dense. Yeah, you're right. It depends on how you define this, and I can't remember exactly what he did, but you know what? I can't remember, but all of them have an inherent density. The material in there it is always chemically denser, but it can become lighter if it gets hot enough. And so what he's using as relative, I can't remember exactly.
Yeah, I guess it depends on how you define the thermal buoyancy. If you
Yeah.
take more temperature difference, or if you take something
It would.
more local.
Yeah. Right. So, but all of these, like typically you can see from here, typically you need, the way he's defined it, you need a buoyancy of 0.6 or larger to get it stable. And all of those are sitting on the bottom because they're dense. So if you don't have some density, then it gets mixed in. Okay. Yes. Uh-huh. Yeah. You mean like this? Like that thing? Uh-huh. Here. Here? Oh, here, yeah. Yeah. Mm-hmm. Yeah, yeah.
But I'm curious about that possibility.
I don't know. Yeah, I don't know the answer to that. But my intuition is that if you made your resolution smaller, that tail would get thinner and thinner. And so that doesn't really answer your, sorry?
It would still go away then.
It would get thinner and thinner. Whether or not it goes away in actual,
Though, like asymptotically,
yeah.
and meet up with the next one.
I think it depends also on some of the, I don't know, some sort of aspect of the internal cohesion of the material or something like that, which maybe isn't represented in here. So you might get into other kind of processes.
Yeah, because the same, that's sort of scale independent in a way, like if ULVZs are compositionally distinct,
Yeah.
this could be ULVZs, and you have that same possibility that they might be ubiquitous,
Yeah.
and then they come
Hmm.
into observational existence where we have, yeah, sufficient resolution.
Right, 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 exactly. Yeah, and so I don't know. Yeah, I don't know the answer to that,
Okay.
but it's a good question. Yeah.
Yeah, another question. I mean, I guess these models you have like walls on both ends. I mean, you cannot go through
Yeah,
them.
yeah, yeah.
So
Hmm.
of course that forces the pile to actually pile up
Yes.
where you have these
Yeah,
walls.
that's right. That's right.
So so on Earth, I mean the real Earth, what would make take that wall? Because otherwise
Yeah.
it would go away,
Um,
right?
well, the way to think about this is reflective symmetry. So, yes, you're forcing it to kind of have a wall here. It's you're in a sense forcing it to have an equal thing on the other side of that wall. And so the way we thought about it was using this. So basically, if you take a cross section across here, across the equator, for example, then you have a slab and an upwelling, and that seems to be uh, symmetrical in that sense. But you're right that it would be good to do a calculation in a full sphere where you put those velocities there. But actually, if you did it exactly, if you had, if had your velocities exactly the way we did it, you'd get the same thing, I think. Um, but you could allow this to move relative to the pile, and geologically you see that happening. And so what effect would that have on it? It'd be interesting to observe that. Yeah. Hmm.
In those models, is the Earth rotating? Do you have Coriolis forces and things like that?
The Coriolis force should not be important for the mantle part of the dynamics. So that would go more in that inertial term that I crossed out because it's 0. So at least for mantle flow, high viscous flow like that, that term should be unimportant.
So the fact that those two big blobs are antipodal sitting at the equator, I mean, don't you think it's sort of acting as
Um,
a sling in that?
yes, but that's a different thing than the Coriolis force.
Right, 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 right.
That's the
But that's the
just maximizing the moment of inertia on. So yeah, if they started to drift off of that,
it would
then the
be,
whole Earth would shift back. But
but that's never in those simulations. You never force the Earth, right?
no, well you could. I mean, no, you don't.
You don't force it.
But the forces from that on the convection would be small. So you don't need to. You can just keep them stable and assume that they're always on the equator. You could look at like if slab material started to accumulate up here and was heavy, would that shift the moment of inertia? That would be interesting to look at.
Yeah, because that is interesting
Yeah.
because you get the effective density of slabs from top to bottom might
Hmm.
be even greater than
Yeah,
the
yeah.
additional clustable density of piles.
That's something to look at, but oops, I'm going the wrong way.
Oh, you have to finish your talk.
Yeah, but I'm almost done. But I guess you would still have that on if subduction were happening around this belt equally, you'd have more on the equator than at the poles. So because the pole area is smaller, so it might not destabilize so much.
And one thing also is that it depends a lot on topography.
Yeah, that's
So
true. The
right,
surface topography, yeah.
surface topography and CMB probably
Mhm.
will have a big effect.
Yeah,
So
yeah,
if you look at the model, that probably.
yeah, yeah. Surface topography, especially because that is way out on the outside. It's far away from the center of the Earth, so its effect on the moment of inertia would be large. Okay, so I'm almost done. Actually, I did that. Yes. And so now we've maybe started to move over here where we're able to, maybe if you assume that Tron-Torzik is right and you can get these piles to be stable over long periods of time, then we can move along in the deep mantle. Maybe we can extend our knowledge of the mantle back farther in time if we kind of assume that stability. And that might allow us to have a reference frame for the rest of the mantle. If those things are stable at the base and the plates are moving relative to them, then maybe we can tease that out. So we could extend some of this modeling back in time. And so that's what I'm going to be doing on the last day, trying to. Another movie from that PhD defense that I went to recently. It's a 2D time-dependent model with free moving plates. There's some similarities to that convective picture that I just showed you. We kind of have two LSVPs with plumes coming up, sometimes from the edges, sometimes from the middles. You have subduction zones that kind of push the LSVP material out of the way. So there's some interesting dynamics there, and sometimes it lands in the middle. So there's some differences and some similarities. If we wanted to find a model that reproduced that aspect of the Earth with two stable LSVPs, we could probably adjust the yield stress and various other things about the model that would produce some sort of model that would more closely resemble the Earth in terms of those things that we were looking at. And so maybe it would stabilize the LSVPs and push the plumes to the edges and things like that.
What about the mathematical notation? We see back and forth, like clockwise and counterclockwise.
Yeah,
Is
yeah.
it real, or is it just because she adjusted
I think,
position remains?
yeah, this is the problem with you putting somebody else's model up there. I don't really know. But my guess is that there are times when the surface motion is going more on average one way, and then at depth, it would move the other way. But, I don't know. Yeah, maybe you know.
I think what I mean, she's using for example is tag YY code, and in that code normally what you do is that you remove any global translation.
Yeah.
So you compute the solution,
Mm-hmm.
but of course the solution is you don't define a global translation of horizontally. You can rotate
Yeah.
that, and you don't want that because in your model, if you start to have that, it can grow very fast and actually faster than the variations
Mm-hmm.
of velocity, which you're actually
Yeah,
seeing
that's right.
in practice. So actually what you do is that at each time step you remove a global horizontal range, and I think that's what makes it, because in fact probably it's moving at the bottom is moving in one way and the top is going in the other. So
Yeah.
your global range stays zero.
Yeah. Yeah. Yeah.
Future extension is right.
Yeah. Yeah. And if you impose a surface velocity that goes around like that, then that's a valid solution. You'd get the whole thing moving around with no deformation. So you always have that as a possible solution. So you have to get rid of that. Okay, but it's so we could tweak our model to try to reproduce these things, but then we would say, well, is that a useful model? It might be useful for explaining those things, but we could test our model against other observations, and this is what Melis did in her PhD defense. She was comparing against observations of dynamic topography. So that's deflection of the surface caused by all this convection, and we have observations of that from the present day, at least, that we can compare against. And plume drift rate. So if a plume moves up through this, how does it move around with time? And so that's another observation we can make. So we can test our model if we get it to work with one set of observations, test it against other observations. Okay, so just to finish out, we can develop models that usefully explain a variety of observations And that, what we've done today is shown models that are useful for understanding general processes. How do plume, why does convection happen? Why do we have two LSVPs, and what sort of type of flow patterns does that indicate? And they give some explanations for the observed seismic and geologic observations. But we haven't yet tried to predict the actual Earth as we see it now. The actual, why do we have a subduction zone exactly here, and things like that. And so what I'm going to do in the next lecture is try to predict actual observations using global flow models. So this is one example of an observation. It's the velocity of plates everywhere. And so we have plates of all different sizes, and they're moving at different rates. And does the flow pattern that we estimate for the mantle predict those motions? Okay, so here are some of the things that we could look at for the present day. Actual observations of the plate velocity field, the tectonic stresses, seismic anisotropy, and the topography. So today I talked about models of mantle convection, the general flow patterns, the processes involved. Tomorrow I'll talk about flow models for the present day. So actually, how is the mantle moving in the present day, and how can we constrain that motion using mantle flow models? And then the last lecture, I'm going to try to take those flow models and extend them backward in time towards using constraints from Earth history. And so, in a sense, this one I'd say is more aspirational. So what we're trying to do is move backward into this area with actual observations from Earth history. Okay, so that's today's lecture, and yeah, thanks. I can take maybe a few questions. It's 10 minutes till the people at the lunch place start getting angry with us. Yeah.
I guess you'll talk about that in the next lectures, but probably your time axis is not linear here, right?
No, it's not.
To get to the
Yeah.
2 billion years, right?
Probably not, but it's hard to make something readable, and yeah.
So what's the,
Yeah.
I mean, just as a teaser.
As a teaser, this, yeah, it's maybe log scale. So, yeah, I would say 300 million years at the extent. So yeah. Okay. Any other questions? Okay. Well, thank you. Oh, sorry.
I was about to ask about what you call long-term stability of LLSVP. So we don't know exactly what it's made of and how it appeared first.
Mm-hmm.
So it's quite complicated to know when it started and how long it lasted.
I agree. Yeah, we don't know. I mean, we observed them to be stable for like the tectonic history that we can reconstruct, which is maybe only 100 million years, then can we extrapolate that back, or how far can we extrapolate it back? Are these structures original from when things started to solidify out of the Earth, and were there always two of them? I think that's a hard question to answer, but if we can understand at least this part, then maybe that'll help us move backward. And
I like this kind of diagram. It's really provocative to fill in the white space. But I imagine like people like geochemists who study, the ancient zircons.
mm-hmm.
People could probably put stuff on there from their field of inquiry with uncertainty, maybe in the up-down direction or left-right direction.
Mm-hmm.
But it would be cool to see how different sciences would put their stuff
Yeah.
just as a stab.
Yeah, and especially if you put an actual time axis here. But yeah, I think that's true. I mean, some people, back from Hadean time or something, you can argue about what's an actual constraint
Well, I mean,
and not. But
even just in the insertion picture, some people say, okay, so
mm-hmm.
go up there now and draw
Yeah, right, and it would be along here maybe, and then when it first started to solidify out, some people think it's solidified in the middle first.
Yeah, in fact, I would like to just mention I remember very well once Claude Allais
Hmm.
presented a slide like that, where he said, okay, geophysics is one thing. Geophysics is all about presence only, like with depth.
Yeah.
Very strict about it.
Yeah.
All depths. Geology is just on the horizontal axis, just surface
Yeah.
strictly, and geochemistry is doing the whole thing.
Okay. Yeah, but in their interpretation, I mean, they are observing things from the surface,
Right.
so they need to have some interpretation to map it downward. But but that's right. Yeah. So, okay. Any other questions? Okay. Great.